All right, today we'll be looking at Coulomb's law and polarization. So we will be drawing charge diagrams throughout this unit, and that just means we'll be showing where the positive and negative charges on an object are as different things happen to it. So we have a couple rules to follow when we draw these charge diagrams. First up, the number of charges in a closed system should stay the same. So that means if I have an object that isn't touching anything else, however many positive charges and negative charges that are on that object at the start need to stay the same. The negative charges can move around a little bit, but we are not going to add or remove charges from that object unless it touches something else. Positive charges can't move, negative charges can move. Any object that has equal amounts of positive and negative charges has a net neutral charge. So this is like first semester, if you remember talking about ions. An ion is when it had an uneven number of electrons and protons. If it had an even number, it just wasn't an ion, it was neutral. So that's what this is. If we have the same number of positive and negative charges, it is neutral. If something has more positive charges than negative charges, then we just say it's positively charged. And if it has more negatives than positives, then it is negatively charged. Again, think back to ions from first semester. So here is an example of what a charge diagram looks like. We have a Van de Graaff generator, which is just something that adds negative charges to it. So here it has 4 positives and 4 negatives. So we would say this is neutral because it's evenly charged here, 4 and 4. It becomes negatively charged. So when you turn this thing on, it brings some negative charges through the outlet and it rides up on this. There's a belt in here and then it adds negative charges to the top. So if we want to show that negatively charged, first up, positive charges aren't moving. So we take our positive charges, we put them in the same spot. If it becomes negatively charged, that means it adds a bunch of negative charges. So we just add a bunch of negative charges onto it. And now we have 8 negatives, 4 positives, net negatively charged because there's more negatives. Here's our second example. We have a neutrally charged gold bar. We have 1, 2, 3, 4, 5, 6, 7 positives and 7 negatives, so it's neutrally charged. It becomes positively charged. Again, the most important rule when we draw these, remember positive charges don't move. So I'm putting the positive charges in the same exact spot. So for this thing to become positively charged, it's not going to become positively charged by adding more positive charges to it. It becomes positively charged by taking away some negatives. So we would remove some negative charges from that object. We'll learn more about that when we learn about conduction. But we remove some negative charges from it, and now all of a sudden we have 7 positives still because they don't move, but we only have 3 negatives. So since we have more positives, it is positively charged. So again, we don't make things positive by adding positive charges. We make things positive by getting rid of negatives. Kind of the same as ions again from first semester. Remember, we didn't remove protons from atoms. That would turn it into a different atom. We would change the number of electrons to make it a positive or negatively charged ion. Here we have a rake. Notice it is negative to start because we only have 3 positives and we have 6 negatives. For it to become neutral, we would need to get rid of 3 of the negatives. So positives stay in the same spot. We add in, or we get rid of 3 negative charges, and now it is neutrally charged. Notice also when we do this, we kind of spread out the negative charges so we don't just stack up all 3 on one side. We just spread them out. And that's how we draw something neutrally charged. This process, if you remember from N1, this is called grounding. When we make something neutral, if we touch it to the ground, we can ground it, and that just means make something neutral. This leads us into Coulomb's law. So Coulomb's law tells us that positive or charges exert forces on one another. So if we have charged particles, they will exert a force on one another. Opposites attract and like charges repel. So that means if I have a positive and a negative charge, they will attract each other. If I have 2 positives or 2 negatives, they will repel each other. That means they will push each other away. So positives and negatives, they will try to get closer together. They will exert a force on each other to pull them in closer. Whereas 2 of the same, so 2 positives or 2 negatives, they will push each other apart. This is called Coulomb's law. If we have charges that are close together, they exert more force on one another. And if we have objects with more charge, so let's say I have something with like 10 positive charges on it versus something with 2 positive charges on it, the system that has the more positive charges will have a stronger force within it. So here's an example. Here we see positive charges, negative charges. They will attract one another. If we have two sets of like charges, so both positives, they will repel and try and push each other away. So here we look at a couple examples. So you can think to yourself for a second, answer these 4 questions. You can pause the video here and just think. Here in A, we have a positive and a negative charge. Here in B, we have 2 positives and 2 positives. C, negative, negative. D, closer together, positive and negative. So think to yourself for a second, answer those questions. You can pause the video here. All right, question number 1, which pairs of charges attract? We are looking for opposites. So A has a positive and a negative. D has a positive and a negative. So A and D will attract. Which ones will repel? Like charges. So B and C. When we have the same thing, they repel. So B and C both repel. Which is the strongest attractive pair? So we have 2 attractive pairs, A and D. So we look, A is farther apart, D is closer together. Remember from the previous slide, charges that are closer together have more force acting on them. So D is the strongest attractive pair. Strongest repulsive pair, we're looking at B or C. Those are the repulsive pairs. C only has 1 charge on each, whereas B has 2 charges on each. So since we have more charge here in B, that's going to be the stronger repulsion since they're the same distance away. So B has the strongest repulsive pair. Our next topic here is polarization. So when we have an object that is close to a charged object, if it is a conductor, it can move its negative charges. So when we bring this positive object close to this neutral object, these negatives can move in it as long as this object is a conductor. So remember, that means electrons can move easily. If it's an insulator, they don't move as much. So when we bring this positive object close, but it's not touching, our negatives will attract to these positives and they will move closer. So remember, positives don't move on our charge diagrams, but negative charges, they will be attracted here and they will move closer. Without touching, they don't actually move over, so they just line up on this side. We call this process, so if we look at this sphere on the right here, this is polarized. So when we have all the negatives lined up on one side and just leaving positives on the other side, we call that polarized. If you remember going back to biology last year, you learned about like water is a polar molecule. One end is positive and the other end is negative. That's because water looked like this. So one end was positive, the other end was negative. So polarized just means charges are lined up on one side, but overall the object is still neutral. Here is what this process looks like in a conductor. So if we bring that positive object close, all the negatives kind of line up on top and then it's polarized. If we bring a negative object, it would just repel them to the other side, and now it's just polarized with them at the bottom. If we look at it in an insulator, the negative charges, since it's an insulator, they move a little bit, but they're not free to move all the way to one end like they are in the conductor. So just remember, a conductor gets a lot of movement of electrons. That's what makes it a conductor. An insulator just has a little movement of electrons because it's an insulator. So now we have a short little simulation you can play around with, and here is what that looks like. So this simulation at bit.ly/PS polarization, if you want to play around with it for yourself, this just shows us we have a sweater, we have this balloon here, and we have a wall. So what I'll do is I will take this sweater, or I'll take this balloon, I'll rub it on the sweater, and through static electricity, I am building up negative charges. So now I have a negatively charged balloon and a positively charged sweater. If I let the balloon go, notice how it attracts right away to the sweater because I have a negative balloon and a positive sweater. So it just gets attracted, and then it sticks. So this is an example of static electricity here. Watch what happens to the charges in the wall. So notice right now, they're all kind of lined up. So this wall is neutral, just a positive next to a negative everywhere. If I bring this negatively charged balloon over to the wall, notice that the negative charges start to move away. So the negatives that are in the wall, they get repelled while the positives stay put because positives don't move. So now we would say this wall is polarized because I have a negative side over here, I have a positive side over here, but notice I have the same number of charges. So if I move it away, nothing has changed in the wall. It's back to neutral, but if I bring this negative object close, it polarizes, and that just means it pushes the negatives to one side, leaving positives on the other side. So you can play around with this a little bit if you want, just to see what the charges look like. You can do it with a couple different balloons, so you can play around with this stuff to see polarization and charging through static electricity here. So this process is just an overview of what I talked through in that simulation. The balloon is negatively charged. It pushes the negative charges away in the wall. That leaves positives on the surface, and then it would actually stick because I have a negative balloon that's being attracted to this positive wall here, or this part of the wall. And that's it for N2.